we are talking about qualitative data. If for statistical test, you have chi-square, we have Yates correction, and you have the Fisher exact test. So first, we're going to do on in terms of hierarchy. I can't really decide. I heard the people pronounce it hierarchy, people pronounce it hierarchy, but I'm going to use the word hierarchy here. So hierarchy, usually we want to use a Pearson chi-square. If Pearson chi-square not valid, then you opt for the Yates correction. If your Yates correction is not valid, then you opt for the Fisher's exact test. Okay, so we always want to use the chi-square first. Chi-square is only valid if there is no expected value of less than 5. So who came up with the chi-square test? The name of the person is Carl Pearson. Okay, he called it goodness of fit test in 1900. He called his test statistic chi-square goodness of fit test. Why the word chi? Because the distribution of this test statistic belongs to a group of skew distribution that he has designated as the chi family. Actually, the test statistic behave like the square of a chi, thus the name chi-square. Okay, so that's the history of the chi-square test. It is the most basic and common form of statistical analysis in the medical literature. You tengoklah mana-mana. Okay, memang chi-square sentiasa ada. Okay, and they do it by doing row and column, comparing the two qualitative data between row and column. R stands for number of rows and C stands for number of columns. What is the point of doing this test? They are used to determine if the two categorical variables are related, whether there's a difference on the rate or between the two groups if they are analyzed together. Okay, by comparing the frequency of cases in the various categories of one variable across the various categories of the other variable. And this variable can have two or more groups. Okay, examples of questions that could be asked in research. One of you was asking, can it be phrased differently? Yes, it can be phrased differently. Okay, for example, the study are trying to see whether males more likely to be smokers than females. Okay. Therefore, the question is the proportion of males that smoke the same as proportion of females? Okay, you are comparing the rate of smokers between males and females. Or you can phrase it as, is there a relationship in gender and smoking behavior? Adakah wujud hubungan di antara jantina dan tabiat merokok? So in this example, we have the gender and we have the smoker. Gender, male and female, smoker, yes and no. There are some assumptions that you have to fulfill to do chi-square test. The samples should be random samples. They are independent observations. What is the meaning of independent observation? They cannot be counted twice. They cannot be counted twice. If you are male, you only have to be counted for male only. You cannot be counted for both male and female. Okay. The other is a sample size be at least 20, and no cell has an expected value of less than 5. Okay, no cell has an expected value of less than 5, and that is a problem. Why? Because many of you do not know how to calculate the expected value. Okay. Very sorry. Okay, so you have this male and female example. We have this disease. So smoking, male and female. Sorry, we have the gender, male and female. Then you have smoking, yes or no. Okay, so if the male smoker, yes, This is the rate of the disease among the exposed. Okay, why? You expect the male to be more likely to be smoker than the female. Then this one is C, rate of smoking, the disease here, among the non-exposed, because you expect female to have a lesser number of smokers. So this is what they call a contingency table, where the risk factor is on the left side. The risk factor is on the left side, the outcome at the top. The outcome at the top, the disease at the top. When you do a chi-square, you do this formula, observed minus expected. So therefore, you need to generate the expected table. Observe. This is the observed table. Okay. Expected is based on the formula A, B, C, then. Okay. So the formula could either be this one for chi-square, but this is only for a 2x2 table. Okay. If it is not a 2x2 table, if it is not a 2x2 table, it is the earlier formula, which is this, observed minus expected. So basically, you determine the null hypothesis, you determine the alternative hypothesis, and you select the alpha level. As mentioned already, alpha level is usually 0.05. You collect the sample, then you calculate the statistics of interest. To determine the degree of freedom, it is the row minus 1 times column minus 1, that is degree of freedom. Okay, then you arrange the data in a contingency table, then you calculate the expected value for each cell. Okay. So basically, at the end of the day, you are going to calculate the chi-square value. You're going to calculate the chi-square value, then you're going to compare the chi-square value against the cutoff point. Okay, against the cutoff point. So here's an example of risk factor, outcome. Okay. So risk factor here is gender, outcome is the disease. So you can see here, this is the rate of the disease among males. These are the rate of disease among females. Rate of the disease among males is here is 55%, female is 45%. So you need to generate the expected table. To generate expected table, you have to do the formula AD over sorry. You have to calculate this one times this one divided by this one. Example, 29 ni. To get the expected value, you have to calculate 96 times 53 divided by 200. And 96 times 53 divided by 200. So they go down, they look right. Angguk, geleng-geleng. So angguk 96, geleng 147, then divide by 200. And that is how you calculate the expected value. So this is explanation on how to calculate expected value for cell A and cell B. Okay. Angguk, geleng-geleng. Because we are testing for the null hypothesis stated that there is no difference of worm infestation between the male group and female group. Expected value is the value if there is no difference of worm infestation between the two groups. Okay. Remember, null hypothesis stated no difference. Tak ada beza. So if this is a study about worm infestation between male and female, the null hypothesis is there is no difference of worm infestation between male and female group. So if there is no difference, therefore the rate should be the same. Therefore the rate should be, for the rate it should be the same. Okay. Tadi for the 55 and 45. So now if it is the same, it is like this. It is like this. So this is the expected. Okay. So instead of 45 and 55, if there is no difference, then it is 48%. So the male got 48%, female got 48%. Bukannya 55 and 45. So it is 48 and 48. So that is how you generate the expected table, by keeping the rate the same. So now you get the difference between the observed value and the expected value. Why? You want to see whether the difference is significant between the observed table and the expected value. Okay? So if there is a difference, then there is a significant difference. If there is no difference, then it means it is the same. The rate of word emphasization between male and female is the same. So, and this is observed, this is expected, divided by expected, and it is repeated again and again for the 4 different cells. You got A, B, C, D, so you got the A, B, C, D differences. Okay? And then you sum them up. Whatever you sum up, that is the chi-square. And the chi-square is 1.303. The cutoff point is 3.84. How do we get 3.84? It is 1.96 squared. 1.96 squared, you get 3.84. Okay, therefore the calculated chi-square is smaller than the critical value. Therefore, the null hypothesis is not rejected. So what does it mean? Male and female both similar rate of word emphasization. So for the 45% and 50%, 5%, is there a difference? Yes, there is a difference. Is the difference significant or not? It is not significant. Okay, by checking the value 1.383, 1.303, it is here. 1.303 is here. Between 0.5 and 0.25. Okay, since it's between 0.5 and 0.25, the p-value is larger than 0.05. Therefore, the null hypothesis is not rejected. Doctor, where you get all this table? This table is from manual calculation of the chi-square. You all got SPSS. Okay, you all got SPSS. Just enter run chi-square, boom, result come out. Doctor, where to learn? I gave you the link already. Go to that link. It is free. Click on how to learn SPSS. Got 6 slides there. Oh, sorry, got 6 videos there. Go through the video and you'll be expert on how to do the analysis. If you still cannot do, look for any UKM graduate. Why? Because UKM graduate, they have SPSS exam. I know it's not fair. The only school of medicine where we expect the undergraduate to perform similarly like the postgraduate. But that's what happened to UKM. So you go and catch the UKM graduates, they can do the analysis. People like exact time no need to come to my class. They all got A's during my class last time. And their exam is the same exam like my master's and PhD student exam. Okay? So they are good. The UKM graduates, they are good. Oh, masuk bakul kat sini. Sorry. Chi-square. If contingency table larger than 2/2, chi-square is valid if less than 20% of the expected values are less than 5 and none are less than 1. Okay? If the chi-square you got expected value less than 5, the number of cells to less than 20%, you're still okay. But if there are more than 20%, your chi-square is not valid. So when your chi-square is not valid, what can you do? You can reduce the number of values. Okay, here's an example. Only 1 cell out of 6 expected value less than 5. 1 out of 6, it is 16.67%. Therefore, the chi-square is still valid. Okay. So in short, I'm just telling you the theory of chi-square. I showed you how to discuss the result of chi-square, but when analyzing, use the SPSS. Yates correction is when the sample size are small. They do Yates correction. But Yates correction can only be done for a 2/2 table. and one of the cells have an expected value of less than 5. So you do like this. So this is the formula for Yates correction. Okay, I'm not going to cover because the whole point here, you can do it inside SPSS. Inside SPSS, Yates correction is known as continuity correction. I repeat, inside SPSS, they don't call it Yates correction, they call it continuity correction. Why? Because Frank Yates is a British guy. SPSS is American software. The Americans hate the British, so they don't use the British names. That's why Americans don't come for Commonwealth Games. Okay, next is Fisher exact test. Don't worry lah. I know last time I like to tell all this story, but today I don't have time. I'm not going to worry about this test. Okay, I'm just going to explain to you. Fisher exact test, you want to calculate, very hard. Why very hard? They use factorial. They use factorial. So please, for Fisher exact test, do not calculate manually. Do not calculate manually because they use factorial. Just take note, when we use Fisher exact test, when sample size is very small. When sample size is less than 20 or when sample size is less than 40. Okay, then you use Fisher exact test. Okay, sample size less than 40 and one of the cell has expected value of less than 5, you use Fisher exact test. Okay, so why I say it is horrible? Because if you do manual, you have to know factorial. This is the formula using factorial. And you have to generate the extreme tables. There are many extreme tables that you have to generate by hand until this value becomes 0. Okay. So this is one calculation. This is the second calculation, third calculation, fourth calculation, until one of the cells become 0. Okay, so that's why you don't calculate Fisher exact test using manual. You use SPSS. Okay, so that is how they calculate for Fisher exact test. And the value that is generated is directly the p-value. So here you can see the p-value is larger than 0.05. Therefore, the null hypothesis is not rejected. Okay. 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 Last. Promise one. This is last test. But chairperson can relax. See, got another 10 minutes. We have the McNemar's test. Who is this McNemar's? It is named after Queen McNemar. Okay. Who introduced it in 1947. Why do we have the McNemar's test? Is like similar like t-test, PET t-test, but instead for continuous data, the McNemar's test is for categorical data, before and after. Okay, before and after. It is a test to compare before and after findings in the same individual, to compare findings in the mesh analysis for dichotomous variable. That's the key point. For dichotomous variable. Examples: attitude statistics before and after research week. Before and after research week. So research week, last time we got 200 students. Before they come for the research week, we give them questions. After they finish the research week, we give them questions again. So what happened? We found out there are people who after attend research week become more stupid. Okay, let's look at the data. When they come to the research week, okay, initially 28 are okay. Initially 28 are okay. After they come to research, after they come to the research week, 42 are okay. So 42 and 28, it looks as though we have improved. But the reality is, of the 28 who first attend the lecture, 8 become less capable of doing statistics. Okay. Of those who were previously less capable of doing statistics, 22 suddenly become more capable. So only 22 people attend class, the rest were sleeping, I think. So anyhow, so this is how they analyze the data inside the McNemar's test. When they run the analysis, they set it as results positive and negative for pre, positive and negative for post. Then they combine them in a contingency table. When they run the analysis, they are looking at the discordant pairs. Discordant pairs are cell B and cell C. Cell B and cell C. The odds ratio is C divided by B. The odds ratio is C divided by B. So odds ratio is C divided by. If B plus C is larger than 25, if B plus C is larger than 25, like here it is 30, so you are okay. Then you use this formula. B minus C squared divided by B plus C. Okay, to get the McNemar's test. If it is less than 25, this one minus 1. Okay, I'm going to show a formula later. So you run the analysis, you put in, you get the McNemar's value 6.533. Then you got the odds ratio 2.75. Then you put it into the table, you get the p-value. So this one is a manual table again. Okay. So you can see the p-value is very significant. Why? Chi-squared 6.53. Okay, it is larger than this value, 3.84. Therefore, it is very significant. So null hypothesis is rejected. Yes, generally there's a better improvement of statistical knowledge among the research week participants, although some gets better and some do get worse. Okay, so there's a significant change in the attitudes of medical students towards confidence statistics before and after the research week. So this one is also available inside SPSS. You don't have to worry. There is no need to calculate this. But just a word of warning, SPSS only use this formula. This formula. SPSS only use this formula. It does not use the other formula. The other formula is for small sample size. When B plus C is less than 25. They're supposed to use this formula. But I already checked, SPSS, they don't care. Less than 25, more than 25, they use the same formula, the other one. Okay. All right. Okay, and with that, I am done. And with that, thank you very much for your kind attention. Okay, I'm going to stop sharing now.